What's going on, guys? Let's look at this problem right here. Here this question is asking, in a certain region the electric field is given by this expression. A part is asking find the charge density, B part is asking calculate the total charge enclosed by the volume, C part is asking confirm Gauss's law by finding the net flux through the surface of the volume in B. Now let's look at the A part. A part is asking to find the charge density. Now charge density can be found using Gauss law. Gauss law says that charge density rho v, that is equal to del dot d. Okay, now del is what? Derivative. So we have to take the derivative of this d with respect to rho, with respect to phi, or like with respect to phi and with respect to z, right? Because we have rho, phi, z components, so we have to take the partial derivative with respect to each components and see what we get, and that's going to be the charge density. Now let's go ahead and do that. So when we do the partial derivative with respect to rho, we have to multiply by 1 over rho, partial derivative with respect to rho, and then rho d rho, okay, and then plus 1 over rho, partial derivative with respect to phi d phi, plus partial derivative with respect to z dz. Okay, now let's go ahead and plug the values. 1 over rho, partial derivative with respect to rho, and then rho multiplied by, okay, first part is we have 2 rho, and if we multiply that one with rho, that's going to be 2 rho square, and then plus 2 rho square multiplied by c plus 1 and cos phi, okay, plus 1 over rho, partial derivative with respect to phi, negative rho z plus 1 sin phi, and that's it for this one, plus partial derivative with respect to z rho square cos phi. Now if you look at this one, last one is a constant because we don't have any z here, so this one will be treated as a constant, and if you take the derivative of a constant, that's going to be 0. So here we are going to have 0 for this one, and for this one except sine, everything else is a constant because sine is the only thing that carries phi. We are taking the derivative with respect to phi, so that's the only thing that's going to change. And for this one, this is 2 rho square is the one that's going to change, others are going to be constant. Okay, now when we do the derivative, we are going to get this one, 4 times z plus 1 cos phi minus z plus 1 cos phi, and finally we will end up with 4 minus 1, that's going to be 3 z plus 1 cos phi microcoulomb per meter cube. So this is going to be the charge density. Now we have done with the A part. Now the second part is asking calculate the total charge enclosed by the volume. Okay, now we have calculated the charge density. We are going to use this one. Now to find the charge, to find the total charge enclosed by the volume, we just have to integrate this one in the volume, in the given region, right? We have the region given for the volume, so we just have to integrate this one in that volume to get the charge, right? Now let's go ahead and do that. Let's get rid of this part. Okay, let's erase this one. Now we are doing the B part. Okay, B part is asking to calculate the total charge, so we are going to calculate the total charge, that's Q enclosed, that's equal to integration V rho V dV. Okay, now the given region is this one. We have 3 regions are given, so the integration is going to go from rho is equal to 0 to 2, and then phi is equal to 0 to phi by 2, and then z is equal to 0 to 4. Okay, so this is what we have right now, and the rho v is this one, 3 z plus 1 cos phi and then here we have to do the spherical coordinate, right? So rho d phi dz. So this is what you have right now. Now let's go ahead and do the integration. After you do the integration by each components, you are going to get 3 rho square to 0 to 2, and then sine phi going from 0 to 5 by 2, and then z square divided by 2 plus z going from 0 to 4. So this is what we get after we do the integration. And if you simplify this one, this is going to end up with 3 times 2 times 1 times 12, and finally that's going to give us 72 microcoulomb. Okay, so this is going to be the final charge we are going to calculate from that. Okay, let's get rid of this one. Okay, now we have done with the B part, and the C part is asking confirm Gauss law by finding the net flux through the surface of the volume in B. Okay, now we are going to confirm this one, finding net flux. So let's note down the value. We have Q enclosed, we calculated to be 72 microcoulomb. So we are going to prove this one by finding the net flux and then recalculating the Q enclosed. Okay, now let's go ahead and do that. We are going to do the C part right now. Okay, and if you draw the cylinder for the given region, it's going to look something like that, something like this. I'm going to draw the cylinder. Okay, and then we are going to have something like this. Okay, so this is what we have right now. Okay, so this is what we have, and we are going to calculate the net flux. So net flux in a closed surface can be calculated using this formula, psi, that's equal to integral d ds. Okay, so this is the equation for the net flux. Now let's go ahead and calculate that one. So this is going to be what, integral top plus integral bottom plus integral surface d dot ds. Okay, so this is what we have to do. Now the flux does not vary along the z, so they are equal and opposite, right? So it's gonna cancel each other, and also the flux from the top and bottom are equal and opposite, so they will also cancel out. So that by the symmetry, the only component is going to be like, we are only going to have the rho direction. That's the only thing that's gonna affect the flux. Okay, that's gonna contribute to this net flux. So we just try to consider the rho axis alone. Okay, now let's go ahead and do that. So first we just try to integrate the surface of the rho surface. Others are going to cancel out. Okay, let's go ahead and do that. So here we are going to have what? We are going to have psi 1 integral surface 1 d ds. Okay, now let's go ahead and copy the function. Here we have d, that's given right here. So this is going to be what, integral surface, and that's gonna be just 2 rho z plus 1 cos phi a rho minus rho z plus 1 sin phi a phi, and then plus rho square cos phi a z. Okay, so this is what we have for d. Now we have to do the integration ds, right? Now we know that only rho is the thing that's going to contribute, so all the other things are going to cancel out, right? So we are going to just left with this part around. This is the only part that's going to remain. Now let's do the integration with that. Let's get rid of this one. Okay, so let's go ahead and do that. So here we are going to have psi 1 is equal to integral surface 1 2 rho z plus 1 cos phi rho d phi dz. Okay, now here we are going to have the region going from 0 to 5 by 2. The regions are given already, 0 to 5 by 2, and then 0 to 4, 2 rho. When we do the rho component, we just have to do the other things. Like when we have only rho components, when we do the integration, we eliminate the rho limits of integral and we do the integration with respect to phi and z. Okay, so here we are going to have a 2 rho times z plus 1 cos phi, and then rho d phi dz. Okay, and after we do the integration, we are going to end up with something like that. We are going to have 8 integral. I'm just doing the inner integration first. So 0 to 5 by 2 cos phi, and then we are going to have z square divided by 2 plus z 0 to 4 d phi. Okay, and if we simplify this one, this is going to become what we are going to have 8 going from 0 to 5 by 8 0 to 5 by 2 integration 0 to 5 by 2 cos phi z square, we plug 4 square first, 4 square divided by 2 plus 4 minus 0 d phi. Okay, and that's gonna give us 96. So finally we will end up with 96 sin phi going from 0 to 5 by 2. So that's going to be 96 microcoulomb. Okay, so this is the charge we are going to have right now. And okay, so this is what we have. So for this one, this is what we have. And also the flux density through the flat surface at phi is equal to 90 degree is going to be what we are going to have sine 90. Like if it's 0 degree, let's look at that one. So we are looking at this one, c plus 1 sine phi. So when the angle is 0 degree, the whole thing is going to be 0. But when we have 90 degree, we are going to have something. So let's look at that one. So d negative rho z plus 1. Okay, let's look at the 0 degree. Sine 0 degree, we will have 0. But if we have a 90 degree, d is equal to negative c rho c plus 1 sine 90. That's going to give us negative rho c plus 1. Okay, so we have something here. So we can also find out part of the flux in this region, right? So in this region, what we are going to do, we are going to do the integration. When we take this is what component, this is phi component. So when we take phi component, we have to do the integration with respect to other two, like z and rho, right? So we have to do the integration with respect to these two, and let's see what we get from that. Let's get rid of this picture, we need some space. Okay, so let's continue on top. So we have this one right here, and we are going to do the integration. So we found out psi 1, now psi 2, another region. This is respect to phi, and z doesn't have components, it's going to cancel out for z. So this is the only thing, this is the last thing that's going to contribute, because we know that rho is going from 0 to 2, we calculated that one, and the phi limit is 0 to 5 by 2. That's why we input 5 by 2 and see so what happened. Now let's go ahead and do the integration. 0 to 2, 0 to 4. So we just do the integration respect to other two when we take the phi component. Okay, negative rho c plus 1 d rho dz, and after you do the integration you are going to get something like this: rho square divided by 2, negative in front, and then 0 to 2 c square divided by 2 plus z going from 0 to 4, and after you calculate this one you are going to get negative 2 times 12, that's going to give us negative 24 microcoulomb. So the net flux is going to be what? Psi net. Let's get rid of this one, or let's write this one right here, psi net. We are going to have psi net, that's going to be equal to psi 1 plus psi 2. Psi 1 we got that one to be 96, psi 2 we got that one to be negative 24, and that's going to give us 72 microcoulomb, and this is what we get finally. Okay, and if you look at the answer we got in part B, is the same thing. So we just proved that Gauss law is correct by finding the net flux and prove this one in that way, right? So this is a long method, but the easy method is the second one we used, right? And that's how we do this kind of problems. I hope this helps. Thanks for watching.